So hello everyone. In this session I'll be explaining a very simple code in order to find all powers of 2 in a given array of data. These are all 32-bit values because I've written DCD, which is define constant double word. So out of this my code will detect all the powers of 2. One thing to note here is this code will detect the powers of 2 starting from 2 to the power 0, that is 1, and all higher values. Okay, it will not detect any negative powers, which in this particular case is nothing but 0.5. So in short, any fractional results won't be detected, only the powers of 2 starting from 1 will be detected. The very first thing you notice here is nothing but the assembler directive area, which defines a section in the memory named as bit tricks. Here I have written code to indicate this particular section of memory shows instructions and it is read only because any modification should not be carried out during runtime on this particular section of memory. Entry is again an assembler directive which informs at which particular location the execution should start. The execution will start at the very first label that appears after entry, which in our case is nothing but start. Okay, so what is happening here? R0 is loaded with the address of the label value. So what is this value? Value is nothing but label associated with our actual array of data. Okay, and R4 will be loaded with the address of the label power of 2, wherein we are storing the final result. If you notice here, I have used an assembler directive space which reserves an uninitialized memory, and 32 here indicates the size, that is memory required to store 32 bytes of data will be reserved. Why I have chosen the size as 32? Because I am considering 8 values. If all 8 values here are powers of 2, then each data will require 4 bytes because it is a 32-bit data. Okay, so 4 into 8 is nothing but 32. That's why I am reserving 32 bytes of data. Okay, and as you can notice here, this section of memory named bit result is read write section because we should be able to modify this content, and it is data section because we are just storing values here. Okay, not actual instruction. Alpha is a counter which has a value stored as 8 since we are considering 8 values in the array. Okay, now let's start with our actual instruction. So what is happening here is content of R0 is actually loaded into register R1. What is content of R0? R0 has the address of this particular array. When this particular instruction is executed, the very first value 0 is copied to R1 and R0 address is incremented by 4 so that in the next loop R0 points to this particular value, that is 1. Okay, so what happens here is the first value is compared with 0. Why it's compared with 0? We know that the smallest power of 2 that will be detecting is 1. Okay, then it is 2, then 4, and this continues, right? Any value lower than 1, that is 0 or negative value, need not be considered in our case. Here the compare instruction performs R1 minus 0. Okay, and based on the result obtained, it will update the CPSR conditional flags. And BLE here is nothing but branch if less than or equal. Okay, so what is less than or equal? R1 if it is less than or equal to 0, in that particular case you have to branch to this particular label wherein just one iteration is reduced and we branch back to the loop. Okay, because we don't want to perform any calculations. Okay, but if R1 is actually greater than 0, which starts from the value 1, in that particular case all these calculations are carried out. Okay, so that is the first thing that you should notice. Next, we'll go to our actual instructions. To understand this, need to know about n and n-1 trick, okay, which is nothing but a very simple concept which explains that for any given number n, if it is a power of 2, then when it is ANDed with n-1, the result should always be equal to 0. Let me consider a number 8, okay, which is actually a power of 2, right? 2 to the power 3. So this in binary is nothing but 1 triple zero. If I AND it with n-1, if n is 8, n-1 would be 7. So if I AND it with this particular value, what is the result? It is 0. Why? Because if you consider each bit position, they have complementary values. And this is true for every case of power of 2. Okay, not only for 8. You can try and check for everything. Okay, so the reason for that is every power of 2 will have only one particular bit set. n-1 will have all the previous bits set as 1. So it's obvious that for any case of power of 2, we will get the result of AND as 0. So this condition is always true except for two cases. One, if you consider n as 0, because 0 ANDed with any number will always be equal to 0. Okay, one more exception case will be 0x8 and all 0. Okay, this is a negative value. That's why I have used this particular compare operation to ensure that these two values are skipped. So now let me continue here. We know we have to perform n and n-1 and check if the result is 0. So the very first thing will be to find n-1. That is done here. So what we are doing is R1 is your n-1 is nothing but R1 minus 1, whose result is stored in R2. Next, the actual AND operation is performed here. This R2 content, which is your n-1, is ANDed with R1 and the result is stored in R3. Okay, in this particular step. And one more thing that is done is and yes is used to ensure CPSR conditional flags are updated. Why do you think it is required? It is required because if this R1 is actually a power of 2, R3 result will be nothing but 0, because of which Z flag will be set as 1. Okay, and that is what we require here. So if in case that is true, the next instruction will be executed. That is, the content of R1, which is nothing but your actual value n, is stored in the location pointed by R4. That is the location where we want to store our result. After that, R4 is updated with R4 plus 4, so that if you have already stored one particular value, in order to move or point to the next location, we are updating R4 with 4. Okay, and then as we expect, that particular iteration is complete, so R5 is decremented by 1 and we are branching back to the loop. This continues until all values are checked, correct values are stored in the location pointed by the label power of 2. Stop B stop is nothing but an infinite loop. Let's check for errors, and since there are no errors, we'll start our debugging session. Okay, so as expected in the first step itself, the address of values is stored in R0. Okay, so let's access that particular memory location. So as expected, all values are stored in the memory, and next thing that we notice is R4 should store the address of power of 2, which is nothing but 4 and all zeros. Power of 2 is just a label. R5 is updated with the value 8 because we have considered 8 values. Loop is nothing but a label. So what is happening in the loop is nothing but R0 content is copied to register R1 and R0 is incremented by 4. So our actual value to be considered is nothing but 0. Okay, so that is compared with 0. And what should happen in this particular case? It is actually equal, so branch will have to this particular label DC. Okay, and here just one iteration is completed. So we are branching back to the loop. The second value in consideration is nothing but 1. Is it a power of 2? Yes. So will this particular branch occur? This particular branch will not occur because 1 is greater than 0. So actual task will start now. So that is first subtraction. 1 minus 1 is 0. So when 0 is added with 1, of course the result is 0. And hence what happens is Z flag will be set. This particular value 1 will be stored in the memory as shown here, and after that R4 is also incremented. Then as expected, we are decrementing the R5 content and branching back to the loop to obtain the very next value from the location pointed by R0. So the control jumps to the actual logic where subtraction happens. 2 when ANDed with 1, result is 0, and hence that value is stored in the memory. You can see both 1 and 2 are stored. Okay, next value in consideration will be 3, but it will fail in this logic because when 3 is ANDed with 2, the result won't be equal to 0. Okay, because of which storing doesn't happen and one iteration is done. Next we have the number 8. Okay, it is power of 2, so branching doesn't happen. Subtraction will generate result 7, so 8 ANDed with 7 generates a value 0, because of which storing happens. Next we have the number 16. So this is again a power of 2. So you can see that getting stored. 10 is the hexadecimal value, decimal number 16. Here I have not written 0x in front of any number, so it's considered as decimal numbers. Okay, so next number to be considered is 35. This particular number is not a power of 2, so it will not be stored. And finally we have the number 64, which is a power of 2, because of which result will be 0 after and storing happens, as you can see here. So then, since all iterations are complete, we are jumping to an infinite loop. Okay, fine. So all the desired power of 2 is stored in the memory. So that's all.